Hi everybody. So in this video, we're going to look at finding the critical region of a Poisson hypothesis test. So we'll work through three questions. The first one will be a one-tailed test, then we'll look at a two-tailed test, and then we'll try an exam-style question. So in our first question, we're told that the number of system crashes over a 10-week period has a mean of 1, and an IT analyst claims that the average number of crashes over that period is now more than 1 due to a recent software instability. She monitors the server over a randomly selected 100-week period to test her claim. We need to determine the critical region for the test at the 5% level of significance. So with questions like this, the first thing we need to do is to state our model. We'll say W, our random variable, is distributed with a Poisson. Now for lambda, if the mean of a 10-week period is 1 crash, and our trial is based over 100 weeks, then lambda will be 10. So that will be 1/10 of the 100 weeks. And now we need to define this random variable. So I'll say that W is the random variable, the number of system crashes over 100 weeks. So now we have our model, we need to state our hypotheses. Our null hypothesis, HO, is that lambda is equal to 10. This is always our null hypothesis. We're testing the lambda given from the question. Our alternate hypothesis is always given in the question. We're told that the analyst claims that the number of crashes is now more than 1. So our alternate hypothesis is that lambda is greater than 10. We'll have a peak at our expected value, which is 10. And because our alternate hypothesis is lambda is greater than 10, we're looking at the tail to the right of the expected value. And this will be our critical region. So if we fall within this region, then we reject HO. And the area of this region is given by the significance level of that 5%, so 0.05. And we'll call that critical value C. So we define our critical region as W, the random variable, being greater than or equal to C, and this has to be less than the significance level of 0.05. And we can find this value C from the tables given in the formula booklet. We can see that lambda will equal 10. Then we go down with probabilities until we get above the 95%, which is here. And then we find the value of x that gives us this cumulative probability. And this is 15. So the probability of being less than or equal to 15 is 0.9513. So if we go back to our notebook, the probability of W being less than or equal to 15 is 0.9513. But we want the probability of the critical region being greater than, so we're in this region. So we're looking for a probability of W being greater than or equal to 16, which is 1 minus it being less than or equal to 15. So 1 minus 0.9513. And when we work this out, we get 0.0487. Okay? So what that tells you is that any value of W greater than or equal to 16 would fall within this critical region because its probability would be less than the significance level of 5%. So our critical region will be W is greater than or equal to 16. Okay? So that's how you find the critical region for a one-tailed test of a Poisson distribution. Let's look at a two-tailed test. Do you want to read through this and highlight the information that you think is important? You can pause the video and come back when you're ready. Okay, so welcome back. So we're told scratches on the phone screens occur randomly at a rate of 2 per 5 centimeters squared. So this is our average. A new packing method is introduced and to test for any change, a 25 centimeter squared sample is inspected. So this will help us define our model. We need to find the critical region at a 5% level of significance. So if we begin by defining y as being distributed with a Poisson, what do you think the average would be? If we're testing 25 centimeters squared, and the scratches occur at a rate of 2 per 5 centimeters squared, then our lambda will be the 2 times the 5. So our lambda will be 10, where y is the random variable, the number of scratches per 25 centimeters squared. And now we need to define our hypotheses. Our null hypothesis is that lambda is equal to 10. What do you think the alternate hypothesis would be? So it tells us here that we're testing for a change, and the change could be greater or less than 10. So our alternate hypothesis is that lambda does not equal 10. So this will involve a two-tailed test. The peak will be at the expected value, and because it's two-tailed test, we're looking at the region to the left and to the right. So we'll have two critical values. I'll call this one C1 and this one C2. What do you think the area under each of these curves will be? So the area under the curves will be half a significance level. So this will be 0.025. So we need to find the probability of y being less than or equal to C1, looking at this region, must be less than the 0.025. And then we're looking at the probability of y being greater than or equal to C2, must be again less than 0.025. And we can work out each of these from our probability tables. Again, we have lambda is 10, and we want the first probability that goes up to the 2.5%. And this will give us a value of x as 3. So this will be the cumulative probability of falling inside that critical region. So a probability of y being less than or equal to 3 was equal to 0.0103. And then we need to do the same for C2. We'll go back to our tables. And now we want the first probability that is closest to 97.5%. And that would be the value when x is 16. This gives us a probability of 0.973. So if the probability of y being less than or equal to 16 is 0.9730, then the critical region will be when y is greater than or equal to 17. This is 1 minus that probability. So 1 minus the 0.9730, and this will give us 0.027. So the probability of being in this region is 2.7%. The probability of being in this region is 1.03%. So our critical region then is when y is less than or equal to 3, or in union, y is greater than or equal to 17. Okay? And then for part B, find the actual significance level of this test. Well, it would only be 5% if this worked out to be exactly 2.5 and this one too, but they don't. This one works out to be this probability and this one is this probability. So the actual significance level will be the sum of the probabilities of the two critical regions. I should have said here this is greater than or equal to 17. So we've got the 0.0103 plus the 0.027. And this gives us an actual level of significance, 0.373. Okay, let's try an exam style question. Okay, so do you want to read through this question yourself? Again, highlighting any information you think is relevant. You can pause the video and come back when you're ready. Okay, so welcome back. So we have a mean rate of 8 crashes per week. And the site administrator wants to find out if the mean rate has increased or decreased. So we're looking at a two-tailed test using a 5% level of significance. So do you want to try and define your model and work out the two critical regions? You can pause the video and then check you're working with mine. Okay, so if we say that x is distributed with a Poisson of lambda 8, where x is the random variable, the number of crashes per week, then we'll say our hypothesis, HO, is that lambda equals 8, and H1, lambda, does not equal 8. And I'll sketch the distribution. We have our expected value, and it's two-tailed, so we're looking at the region to the left and to the right, and each of these areas will have a probability half of a significance level, so with 2.5%. If I call the region to the left C1 and the region to the right C2, then we want the probability of x being less than or equal to C1 must be less than the 2.5%. And the probability of x being greater than or equal to C2 must be the same. So if we go to our tables, we can work out C1. We know that lambda is 8. So we want the first probability that doesn't go beyond the 2.5%. That will be when x is 2. We'll have a probability of 0.0138. So a probability when x is less than or equal to 2, 0.0138. So I'll mark this on the diagram here. To work out C2, we'll go back to our tables, and we want the probability that is closest to 0.975, which is when x is 14. This will be 0.9827. So the probability of x being greater than or equal to 15 will be 1 minus that 14. So 1 minus the 0.9827, which gives us 0.0173. So I'll mark this critical region on the distribution. So for part A, the critical region is when x is less than or equal to 2 in union with x being greater than or equal to 15. And then for part B, find the actual significance level, when this will be the sum of these probabilities. So this one plus this one. And this will give us an actual significance level of 0.0311. And then for part C, during the first week after it was installed, there were 4 crashes. Comment on this finding in light of a critical region. So the 4 crashes would fall within the do not reject region. So we'll say, do not reject HO. There is insufficient evidence that the number of crashes has changed. Okay? Well, thank you very much for watching. If you want more practice on this topic, you can download the worksheet and view the online lesson from my website. I'll leave a link below.